All right. So far, we've talked about mass density and diffraction contrast in the modes that we produce. And so all of these differences in contrast are from differences in the amplitude of the beam, right? We're looking at different sections of the beam, and they have differences in amplitude. However, one of the key features of TEM is this ability to see very small features and to get very good resolution. And typically, what we think of as high resolution TEM or HRTEM. And that is actually, those images are reliant on a different type of contrast. And so I want to talk about that now. And so when we talk about high resolution TEM, we're actually talking about a specific form of TEM that relies on phase contrast. And when we're talking about phase contrast here, we're talking about phase differences, right? In the same way we're talking about diffraction and constructive destructive interference with phase differences, right? It's the same thing here. We're using differences between two phases of the wave to generate contrast. And so this mechanism is very complex, particularly compared to light microscopy. It actually relies on having multiple beams, at least two beams, transmitted and diffracted. But it can often rely on even more beams. And so we will not have time to kind of get into the nitty gritty detail of this, but I'll try to give you a kind of a upper or high level kind of almost hand wavy view of how this works, so that you can kind of understand where these images come from. And so this phase contrast, again, dealing with phase differences. And so the best way to think about it is to think about, again, this is it is for crystalline materials. So again, that's a limitation of it. We can't use this phase contrast on amorphous materials. And so the contrast is generated. We have a crystalline material, and we saw that we had transmitted and diffracted beams, particularly when we saw diffraction contrast. So it's very similar, right, where we have effectively this beam is the one that's diffracted at that scattering angle that we calculated, and then this is the beam that goes straight through. So instead of using that aperture to separate those two beams, either block one or the other to get contrast, what we instead do is we separate them with the objective lens, and we actually let them interact. So we let them recombined. And this is similar to phase contrast imaging in light microscopy, right? We had two different beams, and they recombined and give us differences. And so, we had that outer ring and the inner ring that causes differences in phase between the two paths, and that allowed us to get contrast. Here, it's very similar, but it can be much more complex. But the idea is that we have diffracted beam and the transmitted beam, and we allow them to recombine, and that recombination generates interference patterns, right? So this is the sort of the reciprocal space patterns that you've seen that kind of give us the periodic nature of the crystal. And so those recombined and the phase differences between them give us differences in amplitude. And so this is effectively, if you think back to where I did the laser pointer and the sieve demonstration, it's very similar to that, right? We allowed diffraction to occur, and what you saw was the recombination of those beams around the periodic sieve or mesh, and the recombination produced that spot pattern, which is the reciprocal space component of it. And so the image here is basically a complex version of that periodic nature. So again, we need at least two beams. We need a diffracted and a transmitted beam to allow those to interact. But as I mentioned in the previous section on diffraction contrast, when we used diffraction mode and we were looking at the reciprocal space, we set up the objective aperture on top of only one diffraction spot. So only one set of planes. If we want to represent multiple planes, like you may be able to kind of visualize in these particles here, so you see that there's kind of lines that go this way and then got lines that go diagonal, right? So different crystallographic planes. If you want to represent both of those, you actually need more than two beams. You need the diffracted beam corresponding to these planes, and then you need the diffracted beam corresponding to these planes along with the transmitted beam. So we can use several beams if we want to get more and more complex images in this case. And the result of it is these fringe types, these essentially these what looks like diffracted planes. So what we're seeing with these fringes is effectively each dark fringe kind of it looks like it represents a lattice plane, but again you have to keep in mind that this isn't always a one-to-one correspondence, and so it could kind of represent the opposite, because again these are very complex diffraction interference patterns that are happening, and so but we can measure directly the plane spacing from the fringes, because whether the dark represents in between or the actual plane, you can still use those dark fringes to measure the plane spacing between two fringes. And so a lot of images, you can directly measure the plane spacing from these images using these dark fringes that you see in the image.